All right, welcome to this episode of Current Affairs, the High Power podcast, where we take a deep dive into all things high power energy storage, where it's used in the different industries and different businesses, and the value that it can bring during the energy transition. We're recording from the offices of Skeleton here in Tallinn, Estonia, and this is where we work with customers around the world to support them in solving their challenges around the energy transition and other high power energy needs. If this is the kind of topic that interests you, then I hope you'll subscribe wherever you're listening to this. And if you use high power energy storage to solve any of the challenges in your industry or business, then we'd love to hear from you and maybe have you on here as well. Today, we have Andrew Owens joining us. He's the Global Product Manager for Hitachi Energy's STATCOM business line, and the man spreading the word about the massive value of STATCOMs and why we need them in the grid today. So I'll pass it over to Andrew to maybe give us a bit of an introduction as to what you do at Hitachi and a bit more about your role and how you got into this space in the first place.
Sure. I am what they call the product manager for the section of Hitachi Energy called Grid and Power Quality Solutions. And the segment that I'm involved in is called High Power Solutions. And within that, you have basically devices that support the grid from a stability perspective, both from a series and a shunt point of view. And one of those devices is what they refer to in the industry as an enhanced STATCOM, which is providing grid stability services to the power grid. Been in this industry my entire sort of professional life. Grew up in Hitachi Energy and the predecessor of ABB, and been specifically in this type of FACS is the industry term, flexible AC transmission systems sector since I began.
All right. So the right man to be speaking with.
Sure.
about STATCOMs and grid stability. Well, I've just used the term, and so have you, STATCOM several times. It'd be great to just maybe give a brief overview of what is an STATCOM, and yeah, let's go for there.
Sure. I think if you remember back to your middle school math, you have real and imaginary numbers, and in electricity you have real and imaginary power, and the imaginary power is referred to as reactive power. And so these types of devices operate in the power grid, and this imaginary or reactive power gets absorbed by different loads in the power systems, motor loads like your air conditioning and refrigerator and things like that. And so there needs to be a balance all the time in the power grid when it comes to reactive power capability and active power capability. And so historically, the types of devices that we worked with were restoring this balance of reactive power in an effort to basically keep the voltage stability in the power grid. But now with the energy transition and everything that comes along with that, the grids are a little bit more sensitive to this fluctuation of supply and demand. In the event of some kind of unforeseen circumstance, the impact of an unforeseen event can be larger as we transition to a different generation profile, basically. And so we've kind of innovated away from just being a reactive power supplier in the form of STATCOMs providing reactive power. And we've innovated to incorporate supercapacitors in this instance. And that's what makes it what we refer to as an enhanced STATCOM. And so now with this device, we can provide reactive power support, the imaginary power support. And we can also provide active power support for very short periods of time. And this can basically jump in during events, these unforeseen events, to try to restore that balance between supply and demand and make the impact less.
Maybe, at least from my side, what are these unforeseen events? What kind of examples might we think of?
Sure. So in the power system, you think about, you've got generators, you've got the transmission and distribution grid, and then you've got users, basically. And so you need to think about, from a power systems planning perspective, the entire value chain, basically. You could have an instance where you have a large power generator, like a nuclear facility, for example, that could trip offline unexpectedly.
Okay.
And so you can have this big imbalance between the load, which is the demand side, and the generation, which is the the supply side, and that can create this imbalance. You can also have certain types of events happen in the transmission aspect of things, like lightning bolts or trees
Okay.
falling down on power lines, and then you can have the same thing happen from a user perspective, that perhaps something happened in a large production facility that required the facility to um, disconnect from the power grid, and then if that's a large enough user,
Yeah.
then it can have a pretty big impact in this imbalance between supply and demand.
And are these kinds of instances regular enough or irregular?
I I think by their nature they're irregular. But if we think about like,
Frequent, maybe what I meant.
yeah,
Frequent. Yeah.
I think they do happen, and I think that the positive thing is that from a societal perspective, we traditionally have been well prepared
Mm,
for
okay.
those. From a power systems planning perspective, this is something that the people that provide electricity to us as users are commonly thinking about and planning for these events. What we see is that, as I alluded to before, that like with the same event that happens today or in the future could have a bigger impact in terms of what could go wrong or the effect on the power system as we transition with this green energy transition. That the same event could result in a larger circumstance,
Mm.
basically.
And maybe that was kind of leads nicely on to the next thing I was thinking that so the energy transition towards more renewable energies is, of course, it brings benefits and advantage in terms of, say, maybe CO2 emissions and things like this. But is it also kind of the con side of it is leading to a less stable grid, and this is why the types of technology like these STATCOMs are becoming more necessary, and these irregular instances can have a much bigger impact. And
Mm.
is that
Yes. Basically, when we think about the transition that we're trying to make as a society from fossil fuel based generation to more renewable based generation, then the phenomena that's happening is that we're retiring a lot of large generators.
Mhm, okay.
And what we need to remember is that those large generators were not only providing power that we consume in our light bulbs and the like, but they were also providing a lot of services to the power grid from a voltage stability, from a frequency stability perspective. And so, as we retire those and adopt renewable generation, which is more inverter based as opposed to
Mhm,
machine based, then we need to think about how not only how do we replace the megawatts that were being generated by that generation, but also the services that they were providing, often in an sort of invisible way
mhm.
from a user perspective.
And is this one of the key differentiators between StatComs as they are now and eStatComs? Is that these services can be offered with an eStatCom?
Yeah, so the addition of the supercapacitors as part of the system
Mm,
allows the StatCom to offer more of these
yeah.
services. And so a traditional or conventional StatCom, as we refer to it, was really a stability device. And now with grid forming, it can provide some additional services like system strength and fault current contribution. But it's necessary from uh, a services perspective with regard to inertia and frequency response to have some kind of active power
Mm.
capability so that you can contribute to those aspects of services.
All right. And so the green transition is one driver for the need of eStatComs. But as you were describing earlier and sharing a lot of wisdom with the team here, um, I don't know if it's necessarily a perfect storm, but we've also got AI data centers, which seems to come up in all the podcasts because it's such a massive thing right now. Are these two things coming together, transition to green, and something that requires massive energy requirements? Um, do these make it an even greater necessity for a solution like eStatCom?
Yeah, I think that data centers is, of course, one aspect of it, but
Mhm.
in general, you see this trend toward electrification.
Yeah.
And so a lot of industries that were once relying upon fossil fuels for the energy that's needed to run the process in that sector are now electrifying. And so you're seeing larger and larger point loads, as we refer to them, come online on the scale maybe of even gigawatt
Yeah.
of consumption capability. And so when you couple very, very large users, which maybe become the largest consumer of electric power in the power grid, together with power needing to come from not only alternative sources, but sources that are often geographically located quite far away,
Okay.
then you have this phenomena where you need to what they refer to as wheel power over very large distances, and that's done in the AC backbone of the power grid. And when you have large volumes of power being transmitted over large distances, then when you have events, these events can become exasperated
Okay.
from a circumstance perspective, and that's why you see a large part of our user base basically preparing for these potential events in the form of procuring devices like STATCOMs and enhanced STATCOMs.
And what if these StatComs weren't around? What if they hadn't been developed? What would be the alternative solution, or simply the consequences?
Yeah. So the status quo from a services perspective to provide these kinds of services is to use generators or rotating mass. And when you have a generator, it's providing active power, it's producing electricity, and it's also providing some of these services with its inherent rotating mass. And then there is this concept that's referred to as a synchronous condenser, which is basically a generator that doesn't produce electricity. It provides the services that are associated with a generator, but it doesn't produce actual electrons that can be
Mhm.
consumed in the power grid. So it's purely a stability device. And so that has been the kind of go-to from a inertia perspective for the power system customers to attack these kinds of phenomena when they come up.
Perhaps you'd like to touch upon the. I mean, it was very interesting to hear earlier today that you were touching on the comparisons between the benefits of having, let's say, an active power source such as a supercapacitor as opposed to a rotating mass. How do you see, or how large is the impact that you see from both these technologies being compared?
Mm. Um, so when you talk about a synchronous condenser or a generator, it's kinetic energy. It's rotating mass, and so when you have these kinds of unforeseen circumstances that I referred to, like a generator trip or a large load trip, then what's happening is that physics is kicking in, and when you have a large rotating mass and the frequency in the grid changes, then the machine or the generator is exchanging or injecting or absorbing active power from the power system to help restore this balance. So that's the positive aspect is that the physics kicks in and this phenomena happens. The issue is that you're also a slave to the physics in the form of the volume of energy that can be exchanged with the power system. And so if you take a rotating mass, then you might have a very large installed power capability, but the usable component of that installed power capability during an event can be rather small
Mhm.
due to the physics of needing the change in frequency to be able to exchange the power. And so what we've done with devices like Enhanced StatCom is that we've introduced a power electronic, right, and a sophisticated digital control. And so now with a power electronic and some kind of active power medium, in this case in the form of a supercapacitor, then you're able to, in a very sophisticated way, control the installed active power. And the consequence is that you're able to make use of the entire range of that installed active power. And so the efficiency from a grid perspective of the installed power usability, if you will, is much higher when you have an enhanced STATCOM device compared to a rotating machine.
Right. And you touched on the point of control and protection also a while ago. How would you see both these technologies compared on that front from a controllability point of view and also from the complexity of a protection system, which I believe is very important for the grid as well, right?
So one of the big necessary innovations from a control perspective related to enhanced STATCOM has been the necessity to develop what they refer to as grid forming control. And grid forming control is a different software methodology as to how you behave from a power electronic perspective, sometimes trying to emulate the behavior of a machine. But the positive aspect of having a digital control is that it is digital, it is programmable. And so some of the limitations that you have with a machine is that, once you build a machine, it is a excuse me, a physical device, and therefore it cannot be changed. Whereas with a digital control on power electronics, it's programmable.
Right.
And so the adaptability to the changes in the power grid is much higher with a digital control and a device like an enhanced STATCOM compared to a rotating machine.
And from a lifetime point of view, do you also see the factor of scalability in here? Like, are these enhanced STATCOMs planned in with an option, for example, to grow or decrease in size depending on events in certain areas over the years?
And they could be. I think that's one of the interesting things is that with machines, they're very large devices by its nature, and so once you get to a certain scale of size, then you kick into needing very sophisticated cooling, for example, hydrogen-based cooling, and these become massive installations. Um, and so, for the purposes of handling inertia, it's not super effective. But what we see from a scalability perspective is that we need huge volumes of inertia from a power system perspective, irregardless of the geography that we're speaking about. And so the scalability is definitely there with an enhanced STATCOM to contribute large volumes of inertia and have it be customized to the particular node in which you're going to install such a device.
I was just going to ask, you mentioned a moment ago that with these STATCOMs, they can um, augment the output of a spinning mass, not just about stabilizing the grid, maybe from renewable sources, but they can also support getting more out of the infrastructure that exists today. Is that correct? Have I understood it correctly?
Yeah, I think it's important to know that when you think about the way that we operate our power system, there's basically two limits to how you can operate a power system, and those both have to do with stability. And so, if you think about a power line, for example, it has a thermal capability to transmit electrons along that conductor, and then it has a voltage limit. So there's a voltage limit and there's a thermal limit to a power line. And unfortunately, a large portion of the electrical infrastructure is actually operated due to a voltage stability.
Okay.
And so, what you're trying to do with these types of FACS devices in general and stability devices is you're trying to remove that limitation so that you can operate the existing infrastructure in a better way. And that's really the most impactful when you think about it from a carbon emissions and from an efficiency perspective, that with these types of devices, instead of building new lines or permitting and all the things that come along with that, we can operate the existing infrastructure in a more efficient way. And that's really been the birth and been the mantra of this sector, basically the flexible AC transmission system sector, since its inception, is to make better use of the existing infrastructure.
Well, I hadn't heard that before, and I think that's massive because, as I understand it, for some of the needs of, say, maybe it's data centers or other things coming online, the existing infrastructure isn't there, and to improve it can take 5 to 10 years maybe to do so. But with an e-STATCOM, that can be a solution that kind of bypasses the need for years of infrastructure upgrades.
Yeah, I mean, we often talk about as a transmission planner, which are the people that are dealing with these types of challenges in the power system. There's a number of tools available in their toolbox,
Yeah.
and you can reconductor, you can add transformers, you can build new lines. And what we're trying to do with fax devices is to add tools in that toolbox. And
Yeah.
so often it may not be that it's the silver bullet solution to install a STATCOM or an enhanced STATCOM device, but it's part of a package of solutions that can do, as you say, which is make use of the infrastructure and importantly, accommodate these types of loads that are coming online that are very important in the societal transition from an energy transition perspective.
Maybe changing tack slightly, which markets or countries or governments are currently investing in any STATCOMs and creating that draw from the market for these solutions?
So the kind of market driver or the biggest push that we've seen is from the TSOs in the German market.
Yeah.
And they've been very public in the form of position papers and the like in communicating this need for not only reactive power but also for inertia in the power system. And so you see a number of the German TSOs procuring these devices and have a long-term plan to procure many more. So there we're really seeing the market push from a development perspective.
Yeah.
And it's also kind of an awareness thing that once people see that the market is there and that the supplier base is building up, and why there's the drive from the German market perspective, then they're seeing that there's applicability in all geographic power systems.
Well, that's just the question I was about to ask: is why is there a drive from the German market? Why have they jumped in first and others maybe haven't?
So in this industry, sometimes bad things need to happen to raise awareness of the criticality of these types of things. And I was together writing an article with one of the TSOs related to this technology, and they likened it back all the way to 2007 when there was a system split in continental Europe as a result of a contingency or an unforeseen event. And so often when you have these kinds of exasperated events where large things happen and there's a lot of public attention, then there also becomes a political will to make sure that it doesn't happen again. And that kicks along a lot of studies and looking into these aspects of things. And so you have the transmission system operators not only in Germany but on a European level that are looking into what are our inertia needs, not only today but in 2030, 2040, and these long-term horizons. And so it's important that we have these kinds of entities looking at how will the power system change from a load, transmission, and a generation perspective, and what do we need to do about it in order to accommodate the transition that we want to take as a society.
On that note, what I mean, this technology is, of course, in one way in its nascency. On the other hand, you've done a lot of research development and also deployment of certain portions of this technology out there. But from an innovation point of view, what do you see are like the current innovations being deployed there, and what is the roadmap to, let's say, the next generation of enhanced STATCOMs as well?
So you're right in the fact that a large aspect of these technologies is proven. You're basically innovating upon a base that is a proven base, and that's been born a lot out of necessity. We've gotten these clear requests from the market that we need to do more with these devices, and that's led to the innovations like grid forming and the innovation like enhanced STATCOM. And so that's where we really see the need from a vendor perspective and from a sector perspective that we have to innovate, because it's not a question of if we're going to do this, but it's a question of how we're going to do this. And I think that we're very proud from a Hitachi Energy perspective to step up and create devices or innovate on proven devices to do more with the same topology, the same hardware, and really innovate from a control perspective and add this capability to our devices.
You mentioned that maybe bad things have to happen to get the ball rolling, or maybe that's how at least Germany got the ball rolling for themselves. But you also mentioned when you were speaking with the group here earlier that the kind of TSOs and the grid industry in general is it's very conservative industry, like many industries around us. Um, and this is maybe leading to a slower uptake of the new technology that has clear benefits. But do you see that if Germany picks it up, and as I understand it, they're really going for it, that others will follow when they start to see the value or the benefits that Germany sees? I know maybe the UK is also in the space already.
Absolutely. I mean, someone has to be first, and I
Okay.
think fortunately the German market has really stepped up and been clear that they're willing to be the first. And I think that we need to remember that regardless of how we're going to do this transition, you and I still have the same demands that the lights need to stay on 100% of the time. And so I think it's understandable that you see this conservatism in the industry, because not only are we going to go through this once in a life or once in a generation type shift, but the demand on the power grid remains the same. And I think that kind of challenge cannot be underestimated in terms of what the customer base is going through. With that said, I think that the ball is rolling, and I think once we start to see these things proven in service, then we'll see a larger adoption rate, because the business case is there from a customer perspective. If you have a need for inertia, then this is a very cost efficient way to get large volumes of inertia in the power system.
Is there anything else? I feel like I'm always dragging it back to AI data centers, but the reason that they catch, apart from catch my eye, and apart from that I'm a bit obsessed with AI, is that they have an unusual power needs. Extremely, maybe it's not cyclical. It is cyclical, but necessarily huge draws that maybe aren't as easy for the grid to handle. And do e-STATCOMs support that kind of introduction of cyclical, extremely high peak loads, and then maybe it doesn't need to be something bad to happen, but for something that could mean really great things, like data centers wanting to set up in Europe and other countries that are now, a lot of them claiming we want to be kind of the center of AI. Ireland, for an example, which has a lot of data centers already, but as far as I understand, would struggle to take even one more, let alone an AI data center in the realms of a gigawatt or more power needs.
Yeah, I think that it also sort of remains to be seen what sort of profile we'll see on a grid scale from these types of devices. I personally haven't seen anything in service to where we can see if this will actually come to fruition. I think that stochastic loads by their nature are difficult to handle purely because they are stochastic. And then it gets to, okay, you have the issue of the variability potentially, if that comes to fruition. But they are also very large loads. And so regardless of the load fluctuations that you expect, you also need to be able to be prepared from a power system perspective for that load to drop completely. And so I think that it reinforces this need from a transmission planning perspective that you're introducing contingencies in the power grid that didn't exist before. And with the nature of these loads being so large, they're becoming quite critical contingencies in the power grid. And that's what's driving the demand for these types of devices. So I think you've got the variability in the load, which remains to be seen, whether that will come true. But regardless of that, you've got these extremely large loads that are coming on that we need to plan for the what ifs, basically.
And we talked a little bit about how, say, TSOs and others are a bit conservative in wanting change. Is there anything that you think maybe there are misconceptions about e-STATCOMs that are making people say, hey, I want to wait until someone else does it first? Or is it simply conservatism and they just kind of concerned about change in general?
I think it's a general sort of reluctance to be the first.
Okay.
That's something that we see as a common theme in the industry. But fortunately, there are a number of entities that want to be the first, and we're seeing the positive impacts of that. And so the first movers, I think, are doing a good job of paving the way for the rest of the market and going to provide the showcase for the rest of the world to see that this technology is eventually proven and something that can be rolled out geographically on a broader scale.
And maybe where in the world, if Germany, hey, is kicking off the thing, taking things up first, are there other big markets that are kind of standing in the wings, watching that you've been speaking with, and basically just waiting for Germany to go over the edge, and then there'll be a mass influx, or is it kind of a slow uptake elsewhere in the world?
Well, I think it's have to also kind of pay attention to the way that the power systems are planned. That naturally, these kinds of investments are long cycle decisions, and so this type of technology is launched, in 2020 or around then. And so it's kind of natural as well that it takes a while for the awareness to come available, for the customer base to model these types of devices in the power system and recognize the need. And then you need to get it in the plan, if you will. A lot of these have long-term,
Yeah,
a lot of these geographies have long-term investment plans that need to be approved, either on a political level or from a regulatory perspective. And so, by its nature, these things will take a while to come true, essentially. And I think that we're seeing a portion of that as well. That there's a lot of missionary type work that needs to be to kind of make the awareness there.
yeah, like market education.
Market education for sure.
Yeah.
And then there's a series of events that happens after the awareness, identifying the need, identifying it as a solution, getting the approval, and then the ultimate build out. And that takes time, of course.
So what's an average, let's say, cycle that you just described, like in terms of how long would such a cycle take place?
I think that when you start to talk about a need or identify needs for these types of devices, it's often in like a 5, 10, 15-year plan. Because you have these transmission planners and the like that are looking at how will the power system evolve, both from a load, a generation, and from a transmission and distribution perspective. Um, and then they're identifying it, putting in reports, and then that's getting in the queue, if you will. So it's not unusual that these types of projects can take 5 to 10 years to go from the inception of the idea to actually being something that's built physically.
You mentioned earlier when you were speaking to the group, and it caught my attention of these potential for. I think you said Australia is building a connection to Singapore for a DC connection there, and there's potential that Europe may receive energy from Africa. Do e-STATCOMs support this kind of transmission from, say, renewable energy sources in countries that, say, have a lot more sun, for example?
Mm.
Do these support this kind of global energy kind of provision?
Yeah, I think that there are a lot of ideas now that have to do with what we refer to as high voltage DC, which is something that Hitachi Energy is a market leader in, and so you're talking about taking huge volumes of power and transporting it over very, very long distances.
Yeah.
And so traditionally we operate an AC grid that you and I draw power from. But with certain volumes of energy and with certain distances, the economics to build it as a DC transmission come into play. And we're starting to see a lot more cases where we could see relatively inexpensive renewables be piped via HVDC over very, very long distances. And so you also see trade associations like Seagray, for example, that are looking at what are the benefits, what is the current offering, et cetera, when it comes to enhancing HVDC with some kind of energy storage, whether that's
Okay.
in the HVDC itself, whether it's next to the HVDC, whether it's a supercap battery, et cetera. And so I think the industry at large is asking a similar question as what you said is, can we also apply this technology or the idea behind having active power for very short periods of time to strengthen the business case and strengthen the reliability of these what may have once been thought to be kind of pie in the sky ideas that today in the world that we live in and the world that we want to live in makes sense and is something that we would want to do.
And along those lines as well, what piqued my attention yesterday, of course, when we discussed, was, of course, ancillary revenue sources for such installations. Have you seen or heard or discussed any such possible models where you could use, for example, of course, you have the stability part of it, but any other such models which could be deployed for ancillary revenue for TSOs and, of course, end customers as well?
Yeah, there's an example in the UK, which was an Ofgem funded project, which is the regulator in the UK or a regulator in the UK, where they were looking at using these types of devices for ancillary services. And so, in that particular instance, you had a group of developers that were developing offshore wind and needed STATCOM based devices anyway in order to be able to connect to the grid from a grid compliance perspective. And they were basically asking the question is, can we add devices? Can we augment the devices that we already are purchasing in order to participate in these markets? And right now, there are some regulatory hurdles that are blocking them from participating in those markets. But the charge or the ambition behind the proposal, this incentive project is the name of the project, was to look at what is the benefit to the ratepayer if this future state did in fact exist. As a ratepayer, would we gain access to cheaper or less expensive services, which would then eventually translate into lower power bills?
Right.
And so there is an element in terms of the rollout of this that we also need to recognize that sometimes the technology can make all the sense in the world, but there are regulatory hurdles that are preventing various entities from making use of that technology. And I think that particular project was a good example of challenging the status quo. I don't think that it's reasonable that we expect to do this transition and not change the rules a little bit in terms of how we operate, how the grid is planned, how the grid is operated. If we want to do this, we need to challenge the status quo to accommodate what it is that we want to accomplish from a larger perspective.
This is actually often something we end up touching on is the regulatory environment. Does it support it or does it hold us back? It sounds like at the moment there's challenges around the regulations in place. How likely are these to say change? You say you need to challenge the status quo. We need to push for the change, but this can take quite a while. What's the current kind of situation? Are there significant blockers?
Well, I think that with the current situation, there's a lot about the awareness of the role of this kind of device in the power system. I think sometimes these types of devices get lumped in as energy storage devices, which
Yeah.
could be the wrong categorization of this type of device, because it opens up a can of worms that may not need to be opened in terms of a regulatory perspective. And so it's important that we're educating the regulators as well, that are creating the rules of the game, and educating our customers as to the role of the device in the power system. This is not a storage device that's there for energy arbitrage, for example.
Yeah.
And so it's not energy storage in its sort of most traditional sense. It's actually a transient stability device.
Yeah.
And we have a number of precedents where transmission utilities, transmission operators are capable of purchasing these types of transient stability devices, like a synchronous condenser, for example. And so, if an enhanced STATCOM is playing the same role as a synchronous condenser in the power system, then one could argue, of course, that it's fully within your mandate as a regulated utility or a monopoly provider uh, to procure these types of stability services for yourself.
It's always going to be the challenge when a new technology comes onto the market, and I think we see it ourselves with some of the next gen stuff we're bringing out. Is where does it fall in certain categories? But maybe again, little shift. We in the talk you were giving a little bit earlier to our team, you were giving case of some numbers maybe, and maybe that's my question: is what are some of the measurable benefits in terms of numbers that you've seen with installations that have been tested or up and running?
Yeah, so we have a number of case examples where um, customers come to entities like Hitachi Energy with a set of problems, essentially, and seeking advice on how do you recommend that we go about this. And so we've been fortunate enough to have a couple of real world examples where we've seen customers requesting pretty significant volumes of inertia, and we've been doing comparisons against the status quo, which would be maybe buying rotating machines in the
Yeah.
form of synchronous condensers, and comparing them to what could be done with enhanced STATCOM technology. And there are some cases where we believe that we can do it. We can provide the services that are requested for less than half of what the initial capital cost is. And then there's the lifetime aspect of things as well. That the rotating machines are typically very lossy from an electrical perspective. They have pretty significant electrical losses as a result of the physical rotation of mass, and so these losses costs money. So someone has to pay for those electrical losses, and as we see the importance of losses both economically but also from a sustainability perspective, that um, when you perform a life cycle analysis of this type of device, for example, you see that over 90%, or on the scale of 90% of the carbon emissions over the lifetime of a device like this are associated with electrical losses. And so
That's
if
massive.
you look at, what can we do from a sustainability perspective to really drive down the life cycle cost in the form of emissions of these types of devices, the number one thing you can do is to focus on electrical losses.
That's pretty massive. That it's not only the case that, as far as I understand, these STATCOMs can support bringing online more of the renewable energies into the grid, stabilizing them, and allowing us to use these kinds of green fuel sources or energy sources, but it also drastically reduces the losses and increases the efficiencies of the existing maybe fossil fuel sourced energy storage or energy providing solutions. That's pretty massive. But with that, if is there anything else that makes sense to share that we haven't touched on?
I think in general, with from a Hitachi Energy perspective, this is a very important piece of the market for us, and it's very important for us that we're out there and in the lead, and from a thought leadership perspective.
Yeah.
And so we encourage the public and the customer base to reach out and look for these specific examples so that we can sort of continue to preach the gospel, if you will, related to enhanced STATCOM.
Amazing.
Amazing.
All right. Well, thank you very much, Andrew, for being on the podcast, and for Raoul joining us here as well with some more technical insight than I have, as you may have picked up during the discussion. So again, thanks for listening in and watching. And if you have your own kind of high power energy storage stories or applications that you think others can do with hearing about, then it would be amazing to have you on and share that message and learn. So again, thank you very much.